Today, we're diving into one of the weirdest, most fundamental secrets of the universe, a kind of secret preference that's built right into the laws of nature. But to get there, our story has to start with a crisis. I'm talking about a moment in science when it looked like one of our most sacred principles was just breaking. It's a real cosmic detective story, and the first clue? Well, it was the case of some missing energy. So let's set the scene. We're in the early 20th century, and the crime scene is inside the atom itself. Physicists were studying this thing called beta decay, and honestly, what they were seeing just made no sense at all. Okay, so take a look at this graph. This is the evidence from the crime scene. You see, the law of conservation of energy is a big one. It says energy can't just be created or destroyed. But when scientists measured the electrons shooting out of a decaying nucleus, its energy was almost always less than it was supposed to be. It was as if energy was literally vanishing into thin air. And this was a huge problem. I mean, it was so bad that some physicists were actually willing to just throw out one of the pillars of modern physics. But Wolfgang Pauli, he wasn't ready to give up. So, in 1930, he came up with this really wild idea, something he himself called a desperate remedy to save the law. So, what was Pauli's remedy? He basically invented a suspect, a particle that nobody had ever seen, one so ridiculously elusive it could fly through light years of solid lead without ever bumping into anything. He proposed a ghost. And he called it the neutrino, which means the little neutral one. This ghost particle, he said, gets created during beta decay, and its whole job is to be the getaway driver for all that missing energy. It perfectly balanced the books and saved the day for the law of conservation. Now, it was a beautiful solution, but it would actually take decades before anyone could prove this little particle was real. But just when physicists were finally getting used to this idea of a ghost particle, a whole new mystery popped up. It turns out that solving one puzzle had just created another one. And this one was even deeper. You could say the neutrino was having a bit of an identity crisis. What was happening was scientists started noticing that certain particle interactions, things that looked totally fine on paper, just never happened in the real world. It was like having a key that should fit a lock, but for some reason it just refused to turn. And the clue that broke this new case wide open was this. Neutrinos that were linked to leptons were different from the ones linked to their heavier cousins, called muons. A neutrino made with a muon would only ever interact to make another muon. It would completely ignore electrons. It was like they were in separate, exclusive clubs, and they did not mingle. So this meant there wasn't just one neutrino, there was a whole family of them. 3 different types, or flavors, as we call them. The electron neutrino, the muon neutrino, and later they found an even heavier one, the tau neutrino. But, case closed? Nope, not even close. This just opened the door to an even more profound question. You see, for every particle out there, there is an antiparticle. It's like a mirror twin with the opposite charge. An electron has a positive twin called a positron. But this whole idea created a real headache for a little ghost particle. I mean, think about it for a second. A neutrino has no electric charge. An antineutrino also has no electric charge. They both have this teeny tiny, almost zero mass. So if you can't tell them apart by charge or by mass, what's left? How could nature possibly tell the difference between a particle and its antiparticle if they look totally identical? Well, the answer lies in this really cool property called helicity. Think of it like a secret handshake that only particles know. Helicity is just a way to describe a particle's handedness. You know how every particle is kind of spinning like a little top? And it's also moving in some direction, right? Well, helicity just describes how that spin and that motion are related. Here's an easy way to think about it. Imagine a screw. If you turn it left, counterclockwise, it moves out toward you. The spin is opposite to the motion. We call that left-handed. If you turn it right, clockwise, it moves in, away from you. The spin and motion are aligned. That's right-handed. Particles work the exact same way. In this whole idea of handedness, it wasn't just some minor detail. It turned out to be the absolute key, the fundamental property that finally let physicists tell the difference between a neutrino and its mysterious twin. So a super ingenious experiment was designed to actually measure the helicity of a neutrino. They couldn't see the ghost particle directly, of course, but by watching all the other particles in a nuclear reaction very, very carefully, they could figure out which way the neutrino was spinning compared to which way it was going. And the results were absolutely stunning. No joke. The experiments showed without a shadow of a doubt that a neutrino's spin is always pointed in the opposite direction of its motion. Every single neutrino ever seen was a lefty. So here it is. This is the answer. A neutrino is defined by being left-handed. And the antineutrino, you guessed it, it's always right-handed. This is the secret handshake. It's not their charge, it's not their mass. It's this fundamental, built-in, unchangeable handedness that sets them apart. And this wasn't just a cool theory anymore. It was now experimental fact. The scientists who did the work put it simply. There was no more ambiguity. It was clear that the neutrino and the antineutrino were definitively different particles. And this is where it gets truly mind-bending. For some reason, we still don't fully understand the weak nuclear force, that's the force that runs beta decay, it only interacts with left-handed particles and right-handed antiparticles. The universe, at its most fundamental level, has a preference. In a very real sense, it's left-handed. Which leaves us with one final, massive question that physicists are still wrestling with. Why? Why this preference? Why did nature pick left over right? This little asymmetry might be a clue to even deeper cosmic mysteries, like why there's so much more matter than antimatter out there. But what we know for sure is that this tiny ghost particle, first made up just to solve an energy crisis, ended up revealing a secret about the very architecture of reality itself.